So we're going to do some calculations with the normal density, and this is going to be super helpful. So we usually denote the standard normal random variable with the letter Z. It's just some convention. And the standard normal random variable, if you don't know what it is, it's always a normal random variable that takes mean 0 and variance 1. And this is the density of the standard normal random variable. So fz of x is 1 over square root 2 pi. And then this is e to the minus x squared over 2. And x is all real numbers. So the support is any real number. And we already know that the mean of the standard normal is 0, right? And then the variance is already 1. Because if you want to define a random variable, a normal random variable, you have to know beforehand what the mean and the variance are. But here we want to confirm mathematically that this is the case. So let's do that. So the long way to verify that the mean, so I replaced z by x because I don't like writing z, but the long way to verify that the mean is 0 is just by computing the integral of expectation of x. You know, we did this in another video, but you could note that this expression over here, this is an odd function, this is an even function. So if you take the interval from minus infinity to infinity, then this is an odd function because an odd function times an even function is still odd. So the integral of the odd function is 0. But let's actually compute the integral. And the way you would do this is you would look at this expression over here, x squared over 2, right? So this portion is the normal density. And by definition of expectation, we take the function x and then the PDF over here. And if you look at this expression here, then we can use u substitution. So let's just use let u equals x squared over 2. And then, so that's our integration variable now. And du is going to be x dx, right? So let's just find what this integral is over here. So this is integral of x e to the minus x squared over 2. So we ignore this 1 over square root 2 pi and ignore the integration limits. So this gives us integral of e to the minus u du, right, from the u substitution. So the x dx, right, this part just becomes du, and then this just becomes e to the minus u, right? So this is what we have. And this integral is easy, it's just minus e to the minus u, right? And so this, we want to substitute back what u is. This is e minus e to the minus x squared over 2, right? So this implies that the integral, now let's put the limits back in from minus infinity to infinity. This implies that this integral is so since we excluded the 1 over root 2, let's put it back in. It's 1 over root 2 minus e to the minus x squared over 2 from minus infinity to infinity, right? And this is 0 because if you take the limit of e to the minus x as x goes to infinity, then that's 0 because you're exponentiating a really small number over and over again, right? So the limit is going to be 0. And now let's look at variance. Okay, so note that by definition of variance, this is the definition of variance. We have e of x squared, right? E of x squared minus e of x quantity squared. But here in our normal random variable, e of x is 0, right? So this just leaves us with e of x squared, right? So we only need to find what e of x squared is. And the claim that, of course, the claim is that it's 1. And by definition of expectation, we have e of x squared is, x squared. We take this function x squared, and then we take the PDF, right? 1 over root 2, 1 over square root 2 e to the minus x squared over 2. And then the integration limits, of course, from minus infinity to infinity. The way we do this integral is actually by integration by parts. So it might take you a little bit of thinking, but if you just look at it and think for a little bit, then you might come to the realization that if you let u equals x, right? So we have x squared here, but if you just let u equals x, then you're left with x e to the minus x squared over 2. So again, we're going to ignore this 1 over square root 2. And then if we let dv equals x e to the minus x squared over 2 dx, then this is actually the integral that we just did above, right? So we did this integral over here, right? So this gives us that v equals minus e to the minus x squared over 2, because we did that over here. Right, so this is our integration by parts. And so we have this integral is going to be uv minus integral of v du. And our u is x, right? So we have x and e to the minus x squared over 2. Right. So there is a minus sign here. Right, and then we put back this 1 over root 2, 1 over square root 2. So this is uv. We throw in the integration limits from minus infinity to infinity, and then plus integral of v du, right? And du is dx, so that's just what we have here, and v is minus, right? So this gives us that minus v du is plus integral from minus infinity to infinity of this expression. But what is this expression? This, if you don't remember, is actually the standard normal density, right? So what happens if you integrate the density from minus infinity to infinity? So if you integrate the density over its entire support, then of course this is just equal to 1, right? So of course there's this claim here that this is actually just equal to 0, and let's prove that claim. So there's the claim. And if you know this thing called L'Hopital's rule, then this is pretty easy to show. So to check the condition for L'Hopital's rule, first we check this. So the limit that we want to show equals 0, we can move this exponential to the denominator, right? So it's x over e to the x squared over 2. And if you take the limit of that as x goes to infinity, then this is infinity over infinity. And for minus infinity, this is minus infinity over infinity. So this doesn't change things that much. Okay, so we can apply L'Hopital's rule because x is a continuous function, and x is actually continuous and differentiable, right? So the derivative of x is 1, and that's also continuous. And e of x squared over 2 is also continuous and differentiable over the entire real line. So we can apply L'Hopital's rule. And how do we apply it? Well, you take the limit of this original expression is actually equal to the limit of the top function, the derivative of the top function, which is 1, and then over the derivative of the bottom function, which is x e to the x squared over 2. And this is just 0. Because 1 is 1, and then the denominator is infinity. And then you can do the same thing with minus. It's 1 over minus infinity. So this is also 0. Okay. Now there's something super important. There's a super important property about the normal, which is that if you have a normal random variable, a standard normal random variable, z, so it's standard normal, then if you multiply it by sigma where, okay, so sigma z times z plus mu, then this is actually another normal random variable with mean mu and variance sigma squared. Okay, so this has mean mu and variance sigma squared. We're not going to show that. You can show this, but it's just a little pain. But something that we'll just check quickly is this is actually true for any random variable such that z has mean 0 and variance 1. But we can check this. So expectation of this entire thing, right? By linearity, we can actually divide it into expectation of sigma z plus expectation of mu. But mu is a constant, so expectation of mu is mu, right? And by linearity, you can pull out the sigma. So this is sigma Ez plus mu, but Ez is 0, right? So this is mu. Now variance, we showed one of these properties in the covariance variance videos. So I'll put a link to that up top. The variance of sigma z plus a constant is just variance of sigma z. So the constant actually doesn't add any variability to this random variable because you're just shifting it, right? You're just shifting it. So this is variance sigma z, but again, by the property of variance, if you have variance of a constant times a random variable, then it's the constant squared times the variance, right? But variance of z is 1. So this is sigma squared. Okay. So now this is kind of less important, but if you want to know about how you calculate the moment varying function of a normal random variable, then here it is. So first, let's just calculate it for a standard normal, right? And typically we define the moment varying function as mz of t. Okay, and by definition, it's just expectation of e to the tz. Okay, now to calculate the MGF, we just apply the definition of expectation again. So we take the function e to the tz, right, and then you just have that function, right, and then we want the PDF, right, of z. And then we integrate it from minus infinity to infinity. Now, if you haven't done this integral before, it might take you a while to know what you should do with it. But here is how you would approach it. So you would combine this e to the tx, right? So since e to the a times e to the b is e to the a plus b, we just combine the exponents over here. Right. And there's an observation that you have to make, which is that x minus t squared over 2 is equal to this, right? And that's just from expanding this, right? But you should note that we already have, so if you factor the minus sign, this is minus x squared over 2 minus tx, and then if you divide by 2, right? So this term over here actually, so this term over here is actually already over here. So the moment varying function is actually just, so from this line, we can go to this line. So remember that we actually added or subtracted a t squared over 2 when we didn't have one, so we have to add it back. So we have this e to the t squared over 2. And then this is from what we have just right above. So this e to the t squared over 2 is not does not depend on x, so you can actually just pull it out. It's a constant with respect to x. And now observe what's left. this, if you can identify it, is actually another PDF, but it's actually the PDF of the normal with mean t and normal with mean t and variance 1, right? So this is the PDF of a normal with mean t and variance 1. So this actually just integrates to 1. This entire thing integrates to 1. And now the moment generating function is e to the t squared over 2 for all t, in the real numbers. Now, what if you want to find it for any normal random variable, right? So let's let x be any normal random variable with mean mu and sigma variance sigma squared. Then remember that x equals sigma z plus mu, right? And then z is the standard normal again. Then if you want to calculate the MGF, then we don't actually have to do much. Just here, let's apply the definition of x, right? So that's what we did here. And then let's split up this, apply the distributive property. So let's split up this exponent. So we have e to the sigma t z from this portion, and then e to the t mu from this other portion, right? And this is actually just a constant. There's no random variable here. It's t is a constant, mu is a constant. There's no random variable. So by linearity of expectation, you can pull this out, right? So now here, this is actually the moment generating function. So this is another MGF, but this is the MGF right? So this is mz of sigma t, right? So remember here that we have e to the mz of t is e to the expectation of e to the tz, but just instead of t, let's replace it with sigma t. Then you get actually expectation of e to the sigma tz, right? Now we already calculated the moment generating function for any t. So instead of t, we just substitute sigma t over here, right? So we substitute sigma t, and that's what we get, right? And here's just some algebra, and then we combine the exponents. And this is actually the moment generating function for any normal random variable with mean mu and variance sigma squared, and this is defined for all t. Now here's some basic calculations with the moment generating function. So we found the moment generating function of a normal. Now why do we like moment generating functions? Because they make life easier for us in calculating the moments, the mean and the second moment. So if you take the derivative of the moment generating function, right? So the derivative of e to the f of x is just f prime of x, e to the f of x. So we have the derivative of this, which is, mu plus sigma squared t, right? And then we get back this function, which is mx of t, right? And then if we evaluate this at 0, then remember, if we evaluate mx of 0, then we actually get 1. Because you can plug in 0 here, and we get e to the 0 plus 0, which is e to the 0, and that's 1. And then if we plug in 0 in the derivative, then we just get mu times mx of 0. But this is 1, so it's just mu, right? Now the second derivative, so actually, for any moment generating function, if it exists, or for any moment generating function of any random variable, mx of 0 is 1. So the second derivative, we can apply the product rule. So first we take the derivative of this function with respect to t. This is a constant, right? So we're left with sigma squared mx of t. And then we take the derivative of this right? So we have the same function here, and then m prime x of t. Right, and then we want to evaluate this at 0, and this gives us mx of 0 is 1 again, so this is just sigma squared. This first term is sigma squared, and this is 0, right? So this just gives us mu times m prime of x of 0, but we calculated m prime x of 0, that's mu. So we get sigma squared plus mu squared, right? But what is this? This is actually e of x squared, right? Equals sigma squared plus mu squared, right? And then variance of x is e of x squared minus e of x quantity squared, right? So e of x quantity is squared is mu squared, right? So you just subtract the mu squared and mu squared, and you get the variance is sigma squared, right? That's it.